Good morning, students. We are start our lesson, today's lecture by the new discipline, interchangeability, standardization, and technical measurements. So we start lecture number 1, theme 1, basic concepts of terms and definitions of interchangeability. And please write down to your notes the name of our lecture, theme 1, and the plan of our lecture. First item of our plan is types of interchangeability. Types of interchangeability. Second item of our plan, interchangeability and dimensional accuracy. Interchangeability and dimensional accuracy. Third item or third question of our lecture, rows of predominant numbers. Rows of predominant numbers. And the last item, item number 4, nominal wallet limit sizes. Nominal wallet limit sizes. It's types of sizes, of parts. Nominal wallet limit sizes. I repeat again, please write down to your notes the theme of our lecture and the plan of our lecture. And now we start item 1.1, types of interchangeability. Modern production of machinery and equipment, their exploitation and repair are based on the use of the principle of interchangeability of parts, assembled units, and aggregates. So, interchangeability. Interchangeability is the property of independently manufactured parts to take their place in the assembly unit without additional processing during assembly. Please write down to your notes this definition. Interchangeability is the property of independently manufactured parts to take their place in the assembly unit without additional processing during assembly. At the same time, normal work of products is provided. The principle of interchangeability. A set of scientific and technical provisions, the implementation of which in the design, manufacture, and operation ensures the interchangeability of parts, components, and products. Write down to your notes what is the interchangeability and the principle of interchangeability. You have 30 seconds. And then we continue. Okay. Let's go next slide. So, interchangeability is not provided only by the accuracy of geometric parameters. Interchangeability is not provided only by the accuracy of geometric parameters. Example, the gears are made to the specific dimensions, but some of them do not provide the required hardness of the teeth during thermal hardening. The resulting gears have a shorter service life, and the interchangeability of the assembled components will be violated. The modern direction of interchangeability is functional interchangeability. Accuracy and other exploitation indicators of parts, assemblies, and products must be agreed with the purpose and operating conditions of the final product. Interchangeability in geometric parameters is a private type of functional interchangeability. So, write down to your notes that the interchangeability is not provided only by the accuracy of geometric parameters. The modern direction of interchangeability is the functional interchangeability, and interchangeability in geometric parameters is a private type of functional interchangeability. Interchangeability is complete and incomplete, external and internal. So, full or complete interchangeability allows to receive the set indicators of quality without additional operations in the course of assembly. There are also cases of group selection of parts, selective assembly. The use of compensators, adjusting the position of individual parts of machines, fitting and other additional technological actions when assembling machines. Such interchangeability is called incomplete. It's incomplete interchangeability. Before this was full or complete interchangeability. Was definition. And then external and internal interchangeability. The difference between external and internal interchangeability. And first one, external interchangeability, is the interchangeability of components and components in terms of exploitation parameters and connection dimensions. Internal interchangeability is ensured by the accuracy of the parameters required for the assembly of parts into assemblies and assemblies into mechanisms. So that is the difference between external interchangeability and internal interchangeability, and full or complete interchangeability and with incomplete interchangeability. We finish our first item, and before we start item number 2, interchangeability and dimension accuracy, I want to show to you some videos about interchangeability. What is the interchangeability? Let's try to start video number 1. Video number 1, Introduction to Metrology Measurements.
Measurements are ubiquitous. We consider them in the supermarket to buy the ingredients for our favorite dish. But most importantly, the technology around us measures too many things to know where we are, how the weather is, or even to help us improve our health. Hi, my name is Israel, and today we're going to talk about metrology. Metrology is the science of measurement and its applications. This means it's an area of knowledge that focuses on the study of the theoretical and practical aspects of measurements. But the question now is, what's a measurement? According to the International Vocabulary of Metrology, measurement is the process of experimentally obtaining one or more quantity values that can reasonably be attributed to a quantity. This process is performed by comparing the physical magnitude of the object or phenomenon with a reference unit by using a measuring instrument or a measuring system. The measurements can be used to perform data analysis, monitor a process, or even control it by providing a feedback. Now it's necessary to know what these physical quantities and reference units are. For this, we must talk about the BIPM, the Bureau International des Poids et Mesures, the International Bureau of Weights and Measures. It was born from the Meter Convention in 1875, and it's located on the outskirts of Paris. The BIPM defines the International System of Units, the SI, that has 7 fundamental physical quantities with their corresponding base units. There we can find the mass with the kilogram as base unit, length with the meter, time with the second, electric current with the ampere, thermodynamic temperature with the Kelvin, amount of substance with the mole, and finally, luminous intensity with the candela. As of May 2019, all base units are defined by 7 universal constants that are present in nature and are the same everywhere. Before this, some of the fundamental units were defined from physical objects serving as measurement standards. For example, the kilogram was defined with a platinum-iridium alloy cylinder, known as the International Prototype of the Kilogram, the IPK. If we combine the base units using multiplications and divisions, we can get derived units that allow us to describe the entire universe. Some of these have specific names, such as the coulomb, to measure the electric charge that results from the ampere second. On the other hand, the unit of area does not have a specific name, and it's just square meter. The SI also makes use of prefixes that represent decimal multiples and submultiples of the different units. For example, I can measure the activation time of a transistor in nanoseconds, the weight of an insect in micrograms, or the distance from Geneva to Paris in kilometers. In addition to the International System of Units, the BIPM also ensures traceability, a concept that can be seen in the following way. If I have a measuring instrument, and I want to validate the quality of its measurement, I can take it to a laboratory to certify it. There they will perform a measurement procedure to compare the indication of my instrument with their measurement standard. This quantification process is known as calibration. Once the calibration value, curve, or table along with the corresponding uncertainties are known, if it's outside a specific tolerance range, the measurement can be corrected by adjusting my instrument. It's also important that the measurement standards and procedures of these laboratories are calibrated and accredited by the corresponding national institutes, who handle the national or primary measurement standard. For example, the National Institute of Standards and Technology in the US, the Centro Nacional de Metrología in Mexico, or the Physikalisch-Technische Bundesanstalt in Germany. Finally, the BIPM also ensures that the national measurement procedures and standards are reliable, thereby providing an international standard. In summary, this means that all measurement results are validated through a chain of calibrations or comparisons to an international measurement standard where the highest hierarchy is the BIPM. Speaking of standards, calibration and traceability are defined by the ISO/IEC 17025 standard. ISO is the International Organization for Standardization. It unifies industrial standards and is well known because of the ISO 9001 certification that refers to quality management. The IEC is the International Electrotechnical Commission that publishes standards for electrical and electronic technologies. Both the ISO and the IEC are located in Geneva, Switzerland. In addition, there are some other national standards organizations affiliated to ISO, like ANSI in the US, DIN in Germany, or the DGN in Mexico. Other highly known specific international organizations are the IEEE, NEMA, or the OIML. There are fundamental concepts when talking about metrology that somehow I have already mentioned in terms of the quality of a measurement. They are accuracy, trueness, precision, uncertainty, and error. I will give an example on how to get them and analyze them in a following video. These concepts are also officially defined in different documents and standards, such as the International Vocabulary of Metrology and the Guide to the Expression of Uncertainty in Measurement. Both documents are written by the Joint Committee for Guides in Metrology and serve as reference for the Guide 99 of the ISO and the IEC. The standards ISO 3534, ISO 5725, or IEC 60050 provide more details on these concepts and measuring instruments. To conclude, here are some interesting facts and a question you can answer in the comments. I hope you enjoyed this video. Thank you for watching and see you next time.
And what is mean by interchangeability?
What is meant by interchangeability? Interchangeability can refer to interchangeable parts, the ability to select components for assembly at random and fit them together within proper tolerances. Interchangeability computer science, the ability that an object can be replaced by another object without affecting code using the object.
What is interchangeability in
Like
machine design?
In this video, we are going to discuss about interchangeability in machine design. In machine design, interchangeability represents to the interchangeable parts. So what are interchangeable parts? A machine is a combination of several components. If any of the component is failed or broken, then the part need to be replaced with the new component. This new component should be equal in size to the broken component. These new components can be available from the outside vendors that can be perfectly fit into the position. But how it will be matched with the exact dimensions of the working machine component? Let us see how this is possible. The term interchangeability is applicable for mass production of the components, where these interchangeable parts need to be equal in size, but it's not that easy to maintain that much closeness of accuracy. So these variations should have some limits. Within these limits of dimensions, the components need to be produced in bulk. These components will be within the given limits so that they can perfectly fit into the machine to replace the broken components. These components are called interchangeable parts, and the limits, which are due allowances for the error, are called limit system. This system of limits should be followed to maintain the accuracy of interchangeable parts and provides the required fit. The interchangeability of components helps in reducing the cost of production and also reduce the breakdown time in production if any failure occurs. This is all about interchangeability. Let us know what you think about interchangeability in the comment section below. Thanks for watching. See you guys in the next video. Please subscribe to our channel and press the bell icon so that you will get notified when we post.
And now we are returned to our presentation. And we start item 1.2, interchangeability and dimensional accuracy. Interchangeability of products is ensured by the accuracy of their parameters in particular size. However, in the manufacturing process, errors inevitably occur, the numerical values of which are found by the formula delta x is equal x suffix I minus x, where x is the specified size value. X suffix I is the actual value of the same size or parameter. Write down to your notes this formula. It's formula of error. Errors are divided into systematic, random, and gross. Errors are divided into systematic, random, and gross. First type of error, systematic errors. Systematic errors are errors that are constant in magnitude and direction, or that change according to a certain law. They can be caused by errors in the adjustment of machines, wear of the cutting tools, etc. The influence of these errors can be considered and even eliminated. Next type of errors, random errors. Random errors are errors the magnitude and direction of which cannot be predicted in advance. Their appearance is due to approximately the same influence of a large number of independent random factors. Random errors can be caused by instability of chemical, physical, and mechanical properties of materials, variability of the sizes of preparations, change of forces of cutting, errors of measurements, etc. And the last type of errors, it's gross errors. Gross errors are errors that clearly do not correspond to the processing of measurement process. They are not taken into account. So write down to your notes 3 types of errors: systematic errors, random errors, and gross errors. And please write down to your notes the difference between these 3 types of errors. In the conditions of mass production, the distribution of random errors that occur during the processing of parts is well described by the law of normal Gaussian distribution. In practice, interchangeability is ensured by limiting errors. Write down to your notes that in practice, interchangeability is ensured by limiting errors. And now we start item 1.3, rows of predominant numbers. Rows of predominant numbers. Predominant numbers form series of numbers built on certain laws. The most appropriate are the series built on arithmetic or geometric progressions. More often, apply the series constructed on geometrical progressions. World experience has shown that the requirements of all industries most fully meet the series of predominant numbers that make up geometric progressions with denominators that can be calculated by the formula on your screen. In this formula, x is the exponent of 5, 10, 12, 20, 40, or 80. There are 4 main and 1 additional series of predominant numbers. The degree of the root x is included in the symbols of the series. The 5th row are 5, the 10th are 10, etc. R12, 20, R40, and R80. Please write down to your notes what is the Q. U its denominators, and write down to your notes the formula that we use to calculate this parameter Q. And what values can be used when we calculate these denominators. X can be 5, can be 10, can be 20, 40, or 80. And we have 5th row. It's R5, 10th row, R10, R20, R40, R80. The series of the best numbers are endless. They can be extrapolated to both smaller and larger numbers. The series of predominant numbers served as the basis of the standardization of linear dimensions. There are 4 main series of normal linear dimensions, denoting RA5, RA10, RA20, RA40. ISO recommendations establish the predominant numbers and series of predominant numbers which are decimal series of geometric progression with denominators. For R5, Q will be equal 1.6. For R10, Q will be equal 1.25. For R20, Q will be equal 1.12. And for R40, it's not 20. And for R40, Q will be equal 1.06. Write down to your notes these values of denominators for these 4 rows. First row R5, R10, R20, and R40. R80 series with denominator 1.03 is also allowed. The main series of the best numbers. For R5, Q is equal 1.6, and for R5 we can see first number 1.0, then 1.6, then 2.5, 4.0, and next parameters. Next row, R10, Q is equal 1.25. First item 1.0, second item 1.25, and then 1.6, 2.0, 2.5, and another items. Row R20. First item 1.0, second item for Q that can be equal 1.12, and second item for this row 1.12. Then 1.12 multiplied by 1.12, we can have 1.25. Then multiply by 1.12, and we have 1.4, and another items. And the last one for R40, not 20, R40, Q will be equal 1.06, so first item 1.0, multiply by 1.06, and we have 1.06, then 1.06 multiplied by 1.06, and we will have 1.12. Next item 1.12 multiplied by 1.06, and we have 1.18. And another items of this row we can calculate. Construction of series of normal sizes on the basis of series of the best numbers allows to provide coordination of the sizes of products with their other parameters, with power, productivity, speed of rotation, etc. The system of normal linear dimensions does not apply to derivative dimensions that depend on the accepted initial dimension and parameters, including technological interoperational dimensions. Write down to your notes these 4 rows of predominant numbers. You have 60 seconds. You have 60 seconds. And 1.4 nominal actual limit sizes. Before we start this item of our lecture, I want to show to you another videos. Video number 4. Prefer serious numbers.
It's the basic preferred series. There are 5 basic series designated as R5, which is 5th root of 10, which is 1.58, and we are going to solve numerical on this. The numerical is find out the numbers of R5 basic series from 1 to 10. So step 1 is to calculate the series factor or step ratio. And it is calculated as 5th root of 10, which is 1.5849. The next step is to find out the numbers of the series. First number is 1. 1 into 1.5849, that is, second number is found out as step ratio into N1, which turns out to be 1.5849. We'll round off and make it as 1.6. Third number is step ratio square into N1, which turns out to be 2.51. Fourth number is step ratio cube into N1, which turns out to be 3.98. We will round it off and make it as 4. Fifth number is step ratio raised to 4 into N1, which turns out to be 6.31. And the last number, sixth number, by the same calculation turns out to be 10. So the numbers that we found off are 1 into 1.58. We'll round off and make it off as 1.60, 2.50, 4, 6.3, and 10.
And what is errors? The last video.
This is Stephanie from Statistics House.
Video about systematic error and random error.
Systematic and random error. Systematic error is consistent, repeatable error. On the other hand, random errors, like the name suggests, are completely random. Systematic errors are associated usually with faulty equipment or a flawed experimental design. These errors are usually caused by measuring instruments that are incorrectly calibrated or perhaps used incorrectly. However, they can creep into your experiment from many sources, including worn-out instruments. For example, you might have a plastic tape measure that becomes slightly stretched over the years. Another reason might be an incorrectly calibrated or tiered instrument. For example, you might have a scale that reads 5 when nothing is on it. Another example, you might consistently take an incorrect measurement. For example, you might think the 3/4 mark on a ruler is the 2/3 mark. Systematic errors are always in the same direction. For example, you might be 50 grams, 1%, or negative 20 millimeters off every time. With random errors, it's often difficult to pinpoint the source. There's no pattern. These errors are largely unavoidable and they cannot be replicated. Let's take a look at a couple of types of systematic error. Offset error is where your instrument isn't set to 0. For example, you might forget to tear your scale before you place your items on it. If that tear isn't set properly, all of your readings will have offset error, probably caused by the weight of the container. Scale factor errors are errors that are proportional to the true measurement. For example, a measuring tape stretched to 101% of its original size will consistently give results that are 101% of the true value. Compare those two error patterns with random errors, which have no pattern at all. That's a quick overview of systematic and random errors. You can find more information on our site statisticshowto.com.
It was video about errors, types of errors. And now we continue our lecture. Item number 1.4. 1.4, nominal actual limit sizes. The inner cylindrical surfaces are conventionally called holes and denote big D. The outer surfaces are conventionally called shafts and denote small d. Always, write down to your notes, always. Parameters for the holes, it's big letters. For the shafts, small letters. So, for the holes, big D, for the shafts, small d. Dimensions express the numerical values of linear quantities and are divided into nominal, real, valid, and limit. Dimensions express the numerical values of linear quantities and are divided into nominal, real, or valid, and limit. So, first type of dimensions, it's nominal. Nominal size of basic size. D is the size for which the limit sizes are determined and the deviations are calculated. Nominal dimensions are the basic dimensions of parts of their joints. They are pointed as a result of calculations of details on durability, hardness, wear resistance, and on other criteria of operability. Next type of dimensions, it's real, valid, or actual dimensions, actual size. D suffix R, it's for holes, and D small d suffix R is for shafts. The size set by the measurement with the allowable error. And the last one type of dimensions, it's limit dimensions. Limit dimensions are two maximum permissible dimensions between which the actual size must be or may be the larger of the two limit sizes is called the largest limit size. D suffix maximum. For holes, it will be big D suffix maximum. For shafts, small d suffix maximum. Its largest limit size. And the smallest limit size, d suffix minimum. For holes, big D suffix minimum, and for shafts, small d suffix minimum. Please write down to your notes these three types of size or dimensions. Three types of dimensions. And next slide. The simplify the drawings limit deviations from the nominal size are introduced, which are placed next to this side with the sign plus or minus. The upper limit deviation big yes for holes, small yes for shafts, is the algebraic difference between the largest limit and nominal dimensions. Difference between largest limit and nominal dimensions. Lower limit deviations, big EI or small EI. For the hole, it's big EI. For the shaft, it's small EI. Is the algebraic difference between the smallest limit and nominal dimensions. For the holes, upper limit deviation, big yes is equal D suffix maximum, big D minus nominal size of the holes, minus D. Big EI is equal D suffix minimum minus nominal diameter of the hole. For the shaft, small ES. S is equal D suffix maximum minus D, but D small D suffix maximum for the shaft. It's largest diameter of the shaft. Small EI is equal D suffix minimum, small D suffix minimum minus nominal diameter of the shaft. The real deviation is the algebraic difference between the actual and nominal dimensions. So, it was the last slide. Please write down to your notes this scheme with dimensions, with deviations. And write down to your notes the formulas that we can use to calculate upper limit deviations, ES, and lower limit deviations, EI, for the holes and for the shafts. Please do it now. And now our lecture is finished. If you have the questions, please write to our forum, write to our Telegram groups, and I will see you next week on the next lecture. Goodbye. Have a nice day.